I would like to invite a student who review Professor Kazuto Yamauchi in the first day.
You can raise hand in the list of participants if you already prepared the review of a lecture from Professor Kazuto Yamauchi. Please raise hand and we will call your name to give a presentation.
Is there any? Okay. How about, is there any?
No, I think Mr. Fazli, there's
okay.
no one. Raise hand.
How about a lecture from Professor Henny?
From the second day, Professor Henny Rahmawati. Someone prepare a review from the lecture of Professor Henny Rahmawati. Please raise hand.
Or could you, maybe we should call some, there's one.
Okay, thank you, Lavita Nur Aviana. So for Lavita Nur Aviana, can you please show the presentation? Give a presentation today. Are you ready?
Okay, wait a minute.
Okay, so anytime if you're ready, please start your presentation.
You can start.
Can I start now?
Yes, please.
Okay. Good morning, everyone. My name is Lavita Nurafiana from Department of Nanotechnology, Bandung Institute of Technology, and I will present a lecture resume from Professor Henny Rahmawati with the title Natural-Based Quantum Dots for Theranostic Application. So first, this is the definition of biomass carbon dot, carbon-based zero-dimension material or carbon dots that the source are from eco-friendly natural product such as carbohydrate, protein, or biomolecule that have good water solubility. The advantage for using biomass carbon dots is inexpensive, easy to obtain and abundant, can convert biomass waste into valuable and useful material. So there are two methods to synthesize the BCD materials. First is top down and the second is bottom up. For top down, we cutting the large carbon materials, and bottom up, we fusing the much smaller precursor molecules. Professor Henny give us a lecture about the methods to synthesize the carbon dots with two methods, hydrothermal carbonization and microwave irradiation. For hydrothermal carbonization, the thermochemical degradation of biomass in the presence of water at elevated temperature and pressure. There are two types. The first one is vegetable, and the second one is fruit. This is one of the example from the winter melon to synthesize the biomass carbon dots. And the second one is microwave irradiation. There are two types, chemical oxidation. It using oxidizing agent to oxidize a target by causing the target to lose electron, and the second one is pyrolysis carbonization. This is the common method using reaction process in which a substance is decomposed by heat. Example for plants, this is the some of the example. So from the leaves here, and then for the properties of BCD. The structural, the main component of BCD are nitrogen, carbon, oxygen, and hydrogen to make a various functional group. and then the structure is uniform and dispersed spherical structure, and it has special optical properties of photoluminescence. Because of that, the application, one of the example is for imaging purpose. This is the application for BCD to become a drug delivery, so multifunctional vehicle for drug loading and release. The advantage is highly fluorescent, biocompatible, rapid cellular uptake, and high stability. This is one example for the drug delivery. After that, she tell us about theranostic. So in theranostic, we identify the location of disease, example cancer, for diagnostic image, and then we do the therapy in the disease. So there are two main components, diagnostic and therapy. For diagnostic, it can use radio tracer, contrast agent, particulate, or combination of these three of them. And the therapy is the drug itself to kill the disease. This is one of the example. This is the drug inside the material, and the functionalization with the diagnostic component. So this is the diagnostic agent based on natural products that Professor Henny Labs doing now. So they develop diagnostic agent using curcumin to diagnostic the virus. For example, now is COVID-19, and then after they give the disease to the people with the virus. So this is the timeline, and that's all for me for the resume of Professor Henny lecture. Thank you.
Thank you, Lavita. Is there any short questions? Maybe one question from participants? Is there any? Okay. Do you have any questions?
If there's no questions, so we can continue to
next presenter.
Yeah, next presenter is Alif Irham. Alif Irham will give a review of a lecture from Professor Chong Tan Bah. So for Alif Irham, hello, can you hear me?
Oh yeah, okay, I can hear.
Okay, Alif Irham, so please start your presentation anytime you're ready.
Okay, let me search my screen for a second.
Okay, you already become co-host.
Alif.
Yes.
Can you turn on your camera? I would like to know your face.
Oh yeah, sorry.
So we are in the same department.
Okay.
Okay, now I know you.
Okay. Everyone see my screen?
Yes. 5 minutes. No more.
5 minutes. Okay. So let me start my presentation. Good morning to all participants and IVC committee. At this occasion, I would like to present my review regarding the lecture from Dr. Chong in the model for finite temperature properties of the cobalt niobium oxide. I'm sorry, but in the last lecture, I can hear clearly, and the time is so limited in the second part, so I will just discuss about the first part of this lecture. So in the first part of his lecture, he's telling us about the transverse Ising magnet, and the transverse Ising magnet is in the transverse Ising magnet, a magnetic field. When we apply a magnetic field in applied transverse to the easy axis, the spins induce zero Kelvin phase transitions. This phase transitions is very related to the quantum critical point, and the materials that we observe here is a cobalt niobium oxide. when it have a Ising chain. The Ising chain is a one-dimensional chains that will have very interesting properties in these materials. So what is the quantum critical points? The quantum critical points is a point where when the physics properties of a materials is changing, which we can see by this figure, where can we see that the ferroelectric changing to the quantum paraelectric by tuning the parameters. In the quantum critical points, actually there is some properties that we can change. That there are temperature, atomic concentration, and the pressure itself. And we also can relate the quantum critical points with the transfer Ising magnet. And his second lecture, we can see that the Professor Chong telling us about atom concentrations of some dopant into the lanthanum materials. So if we want to see the transfer Ising magnet and the quantum critical point, there is some issues regarding this. Then we can see that there is a problem in the Hamiltonians, and the Hamiltonians is very related into the exchange parameter here, limited by J, and then the spin itself. So what does the transfer Ising magnet cause here? We can see that in these materials, the cobalt niobium oxides, we can see by the increasing the magnetization, the external magnetic field with the temperature, we can see that there is a saturated phase in the system. Then if we can increase the magnetic field from the higher than 5 Tesla, we can see that there's a change from the ordered material to disordered materials. So if we plot this graph into the x-axis into the external magnetic field, we can see that there is some critical points. These critical points is observed within the specific heat capacity. Then there is some unique properties that we can see that below the 1 Kelvin, the gapless modes display a temperature linear heat capacity similar to the fermionic excitation. So how to see the contribution of spin here? The spin contribution should be calculated by using these equations. Then by analyzing the specific heat capacity with the variation of temperature, we can see that these models, which draw by the dashed line, could fit the experimental data that we obtain. Therefore, we can also calculate the spin entropy to see within which degree of freedom of spin is acting in this material. So we can see that by integrating the specific capacity, we can obtain the large anomalous peak center at the quantum critical points is from the one third of the total spin density of degree of freedom. And from this, we can see that the entropy infer the account for nearly the total spin degrees, and we can see that in the below 1 Kelvin and with the changing the quantum critical point, we can see that there is a fermion-like heat capacity, and we can see that there is several interesting properties. So I think that's my presentations. Thank you very much.
Thank you very much, Mr. Alif Irham. So it's already 5 minutes, so we will continue to the next presenter. The next presenter is Falika Balkis to review Dr. Grand Prix TM lecture. So for Falihah Balkis, are you ready to give a presentation?
Yes.
Okay, so please start now. You can start now.
I can share my screen.
Oh, okay. Now maybe you can try again to share screen. Can you?
Yes.
Okay, so please start your presentation.
Okay, good morning, everyone. Today I would like to present about a lecture from Dr. Grand Prix TM Kaja. It's titled Nanoporous Materials Synthesis and Catalytic Application. It's a lecture review from me. So during the lecture, I took some notes, and this is my summary. The first one is the definition and types. Nanoporous materials are inorganic or organic materials which have pore size of less than 100 nanometer. The types of nanoporous materials are, the first one is micropores. It has less than 2 nanometer size. It's formed from materials. The first one is zeolite. It has large surface area with tetrahedral units, or T4. Actually, T here, it means as silicon and or aluminum. And it's synthesized from amorphous aluminum oxides, silicon dioxide, and water, alkaline, and organic structure. These ingredients are heated hydrothermally, and then the crystalline zeolite is formed. The second materials is metal organic frameworks, or MOF. The 2D or 3D structure is formed from metal ion or cluster and organic ligands or linker. It's more diverse than the zeolites. And the third one is covalent organic frameworks, or COFs. Its giant organic molecule is formed from organic molecule and organic ligands. It has high flexibility to control their physical properties. The second nanoporous material size is mesoporous. It has 2 to 15 nanometer size. The materials that forms the mesoporous nanoporous materials is silica or carbon-based. The silica one is amorphous and it has evenly distributed pores. But the carbon-based, it has 2 pores distribution types. It can be ordered or non-ordered. The mesoporous nanoporous materials is synthesized by soft templating or hard templating process. Then the third one is micropores. It has 50 to 100 nanometer size. It can be formed from carbon or silica or alumina. And the last one is hierarchical porosity. It means it consists of more than one pore size among the 3 above. It can be micropores, mesopores, or macropores, which are interconnected and form a distribution of inlet flow. Why hierarchical porosity is important? Because it relieves mass transport, boosts catalytic performance, and it extends applications of zeolite into new areas. And it is synthesized using bottom-up or top-down process. The bottom-up is using mesoporogen, while the top-down is using desilication and or delamination process. Nanoporous materials is characterized using XRD, X-ray diffraction, to characterize its crystallinity and elements, or gas phase absorption, or scanning electron microscope, or transmission electron microscopy with selected area electron diffraction to characterize crystalline and crystalline uniformity. The example result is right here. And the application of nanoporous materials is very wide, but the one that is focused in this lecture is catalysis. Nanoporous materials are used in fluid catalytic cracking process in petroleum refinery. It converts petroleum crude oil into products using shape selective reactions of zeolites. And this is the conclusion for me. Nanoporous materials are widely used in many fields: fuel cells, solar cells, biological stuff like drug delivery, cell biology, sensors, devices. But like I mentioned before, the one that is focused in this lecture is catalysis. The nanoporous materials is different from nanomaterials because nanomaterials has nano-sized materials, but the nanoporous materials has the bulk part and the pore inside it. And the third one is their applicability depends on their targeted design at the atomic and molecular level. which controls their porosity and surface area. Okay, that's all from me. Thank you.
Thank you very much for Falihah Balkis for your presentation. The next presenter is...
Is there any questions?
Oh, there's any question? Sorry. Is there any question for Falihah Balkis? Okay. If there's no question, we continue to the next presenter, Rai Rona. Can you hear me? Rai Rona will present a review from Dr. Nasrullah Tabatei. Rai Rona, are you ready to present?
Yes, I'm ready. Can I share my screen?
Okay. So
Yes.
if you're ready, please start your presentation 5 minutes from now. I mean, 5 minutes is a time for presentation. Thank you.
Can you see my presentation?
Yes, we can see.
Okay. Good morning, everyone. Good morning, everyone. I'm Rai Ronaldo from Nanotechnology Institute Technology Bandung. I will review a lecture from Dr. Nasrullah Tabatei, that titled Magnetic Nanoparticles and Their Biomedical Applications. So first, I will give a review about physics of magnetic materials. In an atom of a materials, magnetic field is produced by orbital motion of electron that acting like tiny electron current loops. With a right-hand rule, we can know the magnetic property of this motion. And next, there is a range of a small unit where containing atom with single parallel direction or similar parallel direction that called domain, magnetic domain. And between each domain, there's it's separated by a wall called Bloch wall. And inside a wall, the magnetic moment is rearranged to minimize the energy. If we place this material in the external magnetic field, the magnetic moment will try to align themselves with the field direction. And how the material behaves to respond to the external magnetic field is called magnetic susceptibility. And that defines the magnetism of the materials. Magnetism can be categorized by diamagnetic, paramagnetic, ferromagnetic, and ferrimagnetic. The left curve is hysteresis curve. This curve shows the response of the magnetization of the material that exposed by external magnetic field. We can see there is a delay that happens of the material when the direction of external field is switched or when the magnetic field is removed. This phenomena called remanence. And there is a relation with the temperature. There is a specific value of temperature that perform zero remanence, and this temperature called Curie temperature. In the next curve, we can see the different type of magnetism: ferromagnetism, diamagnetism, paramagnetism, and superparamagnetism has a different curve. Uh, we can focus on blue line curve that performs superparamagnetism. In this curve, we can see there's no remanence occur when the extramagnetic field is switched. So superparamagnetic properties are very desirable for biomedical application because we don't want the magnetization of a material inside our body is still remain when the extramagnetic field is removed. And this property can be obtained on single domain material and can be reached in nanometer size grain diameter. The common application, biomedical application that have many discussion is FIANs, superparamagnetic iron oxide nanoparticles. And the synthesis of this FIAN can be conducted with several methods like co-precipitation method, thermal decomposition, microemulsion, or sol gel. And also we need to add surfactant to prevent agglomeration that happen either because static or electrostatic effect. we can coat the material with some other material, organic or inorganic, and also surfactant can introduce addition binding site to the magnetic nanoparticles. In biomedical application, we can divide it into two types, therapy and diagnosis. In therapy, first example is for drug delivery. We can inject the magnetic nanoparticles that contain drug to our body, into our body, and directing the material with external magnetic field, usually combined with MRI, to a specific part of our body or specific organ. The other method to inject the material into our body is using aerosol droplet containing magnetic nanoparticles. So we just need to inhale the material to inside our body and also directing it using external magnetic field. The other application is therapy for hyperthermia. And in the other side, in diagnosis, we can use magnetic nanoparticle in biosensor. Many research was conducted and conclude that magnetic nanoparticle can enhance some type of biosensors. And the other application is transfection and many more. So that's all for me. Thank you.
Thank
Thank
you.
you. Is
Thank
there
you,
any comment or question from participants?
maybe also from the lecturer
Yes.
who joined with us today. If there's any question from Sensei from Osaka University or professor from Institut Teknologi Bandung or Vietnam, Chanto University.
You can ask the presenter.
Yeah.
Okay. Maybe what short announcement. A few minutes ago, I shared to you the attendance form. Maybe you cannot find your name in that form because actually that's for only for the IVC participants. Only for the IVC participant. Thank you. Maybe we go to the next presenter.
Okay. Before that, I would like to invite also the OUICP student. If you want to give a presentation today about additional topics you brought, so please write your name in the chat room. We will call you following the QA of the presenter.
Yes.
And yeah, we're very welcome. If you want to give a presentation of your topics, we were very welcome. And then for the next presenter, Domenico Michael will give a presentation about the review from Professor Yasuhiro Sugawara. Domenico Michael, are you ready?
Yes.
Okay, please start your presentation.
Okay. Can my slide be seen?
Yes, we can see.
Yes.
Okay, so good day, everyone. My name is Domenico from Materials Engineering Department in ITB. And now I want to share some summary from Professor Yasuhiro Sugawara lecture, which entitled Manipulation of Surface Atoms and Charged States by AFM. Okay, before Sugawara Sensei brought us 4 main topics. The first one is about AFM, or atomic force microscopy. It is a microscopy technique that uses the interaction force between two atoms, and it will obtain a true atomic resolution images. And one of the AFM advantages are it can measure the force and the energy. So this figure show the interaction between the tip atom and the sample atom, and these are the curve. There are two types of force in this interaction. The first one is the long range, which consists of van der Waals and electrostatic force. And the other one is the short range force, or the chemical binding force and the Pauli repulsion. So how do we measure this interaction force? we use this kind of method. It's called a frequency modulation method. These are the schematic. In short, this cantilever has its initial frequency of F0. When it is approaching the sample or interacting with the sample, this frequency will shift like this to become F1. So by using this kind of information, the frequency shift, we can measure the force or the energy. The second one is about the atom manipulation on copper oxide surface. He used two different tips. The first one is the O adsorb tip, and the second one is the copper adsorb tip. And this different type of tip will give a different result in atom observed and the force and the manipulation type. So from this kind of experiment, we can conclude that the chemical nature of the tip sample interaction will play an important role in atom manipulation. Okay, the third one is about two-dimensional force spectroscopy. So this is the atom coordinate, and these are the sample atom coordinate, and these are the potential energy, and above it are the tip of FM. So when the tip is approaching the sample, there will be an attractive force between them, and this will change the potential energy of the sample. So the barrier energy from this high will be decreased like this. So the atom can move to the neighboring side. And this kind of interaction, as I mentioned before, will create a frequency shift in the FM tip. And using this kind of formula, we can calculate that the force from the frequency shift. But remember that this force consists of two types of force, long range and short range. So we need to subtract this total force with the long range force, so we can get the short range force, specifically the chemical binding force. So these are the next diagram. From the total force, we subtract with the long range force to get the short range force or the chemical binding force. And after that, we can we can calculate the energy using this formula. And last is about the manipulation of charge states on titanium oxide surface. So in here, we use Kelvin probe force spectroscopy. And this spectroscopy is based on electrostatic force. So the frequency shift will depend on the bias voltage we apply. So we apply bias voltage from this range, from this plus to this minus. And from start is the red line here. And with the decreasing of bias voltage, we can, at a certain point, we can see that the electron from the sample will transfer to the tip. And this kind of phenomenon will create a frequency jump like this. And when we reverse the voltage or increasing the voltage, the reverse happen. The electron from the tip will transfer to the sample. So by using this kind of electron transfer, as we may know that charge is related to the electron, by using this kind of principle, we can successfully manipulate the charge and the binding state of oxygen atom on titanium oxide surface.
Sorry, 1 more minute already.
Okay, I think that's all from me. Thank you.
Thank you, Domenico. Is there any comment or questions from participant?
I have a question.
Yes, please, Sensei.
What is Sugawara Sensei's lecture related to your research subject?
Please, Domenico.
To my research subject? Do you mean?
Yes. Do you
Oh,
research stuff?
no, no.
Not, then what is the reason why you choose this subject? You want to study this subject or just for just you are
Actually,
interested?
actually for ITB student, it's the topic given to me.
Oh, I saw. So, okay. Good. Thank you.
Okay. Thank you, Domenico. Maybe we move to the next presenter.
Next presenter will be Albert Timothy.
Yes.
He will review the presentation from Dr. Grant Prix M. Kaja. So, Albert, are you ready to present?
Yes, I am ready.
Okay, please start your presentation.
5 minutes.
Okay. Is my screen can be seen?
Yes, we can see your screen.
Okay, good morning, everyone. My name is Albert Timothy Lasiman from Department of Engineering Physics, Institute of Technology, Bandung. Today, I will be reviewing Dr. Grant Prix lecture with the topic of nanoporous materials, the synthesis and catalytic application. First, nanoporous materials are materials with porous size less than 100 nanometers. So the parameter to classify a material as nanoporous is based on the porous size, not the material size. The nanoporous materials can be classified into 3 categories based on the porous size. The smallest is the microporous, with porous size less than 2 nanometers. The example is zeolite, MOFs, or metal organic frameworks, and covalent organic frameworks, or COFs. Then there is also mesoporous with porous size 2 to 50 nanometers. For example, there's mesoporous silica and mesoporous carbon. And the third one is macroporous with porous size greater than 50 nanometers. For example, macroporous silica and macroporous carbon. You can see here that the material for mesoporous and macroporous, there's also silica and carbon, but the difference is the porous size. So they are fall into 2 different categories. I would like to introduce also there's hierarchical porosity. Hierarchical porosity is when a material has more than one porosity. For example, if a material has a microporous and also a mesoporous, or microporous and also macroporous, or 3 of them at once. But beside more than one porosity, porosity must also satisfy the interconnectivity and distribution of inlet flow. Interconnectivity means that the porosity is interconnected with each other, and the distribution of inlet flow refers to when molecule, incoming molecule materials, the incoming molecule pass the bigger porous first, then to the smaller porous. For example, the incoming molecule must pass the mesoporous first, then microporous. And in this review, I will focus on the zeolite part. So we'll move to the synthesis of zeolite. The synthesis of zeolite is quite simple. First, we need to prepare the materials. Zeolite is aluminosilica crystalline. So first we must prepare this SI source, ALS or STA. The process is quite simple. We combine all the materials to autoclave, and we will use the hydrothermal. It means that there is water as the solvent, and the temperature will be above the boiling point of temperature of water. So it's, and then we will get the crystalline zeolite. So the process is quite simple. I will like to give a brief why we use alkaline source and OSDA. We use alkaline source to make the crystalline. So first the zeolite is amorphous, and we need alkaline to the zeolite to crystal, because the alkaline will give the process of hydrolysis condensation, and OSDA act as the template. So the hydrolysis and condensation process will take place around the OSDA. The zeolite will form around the OSDA. Next, I want to introduce also the hierarchy of zeolite. So we want to introduce mesopore to our zeolite. First zeolite is micropores, then we would like to introduce mesopore, bigger pore to zeolite. There's two major strategy. First is bottom up and second is top down. Bottom up method, also called the constructive method. In addition to OSDA, we also need mesoporogen or mesoporous generating agent. So we take carbon nanotube, the mesoporogen then will act as the template instead of the OSDA. The process of hydrolysis and condensation around the carbon nanotube. Then we will remove the carbon nanotube because the zeolite is aluminosilica crystalline, so we will dissolve the silica or the aluminum. If we want to partially dissolve the silica, we can use alkaline, or if you can use acid. And the last part is the application of zeolite catalyst. Okay. The properties of zeolite is the three is this molecular shift. So the zeolite can act as then zeolite also have ion exchange ability that will lead zeolite to strong acidity. But there is a difference because zeolite is it will catalytic performance. And that's all for my presentation.
Hello, Albert. Albert.
I think we lost your connection.
Yeah, I think there's a trouble in Albert Timothy's connection. Hello, Albert.
Yes.
Can you hear me?
That's all for my presentation. Oh,
is there any question or comments?
Yeah, yes. Anyways.
Okay. Is there
I will.
Okay, maybe we wait for a question or there is any question or comment? I think no.
No. Thank you very much, Albert, for your presentation.
Thank you. Maybe we want to call one student from OUICP group.
Okay.
Before we continue the list in the Zoom chat, I will call your name randomly. Maybe Miss Yanmi, could you present your report?
Yeah, I'm here.
Yes.
Are you listening? Do you listen to me?
Yes,
Yes.
we can hear your
Can you
voice.
show your, can you?
Yes, I
on
share
your
now.
camera?
Yeah, wait a moment.
Okay.
Yeah.
Oh, in the list also you already write that Miss Yanmi will give a presentation from Professor Sato and Professor Dino.
Hmm.
Do you see my screen now?
Yes.
Yes.
Okay.
You have 5 minutes, please.
Yes, I begin. Yeah, according to the advice of our SIP program, now I choose two sections, and that is section 3 and section 5. First one, I want to talk about the section 3. It's about the design of magnetic materials for spintronics. Yeah, there's the outline of this section. First one, we have definition, spintronics and TMS system. Spintronics is when spintronics is a kind of property that we pay attention about the electron track and electron spin. And TMS system is a kind of material that it has a spintronic property. And the method we use to calculate TMS system is a KKR CPI method. CCA method gives us an average properties of this other system. And KKR method is a calculate electronic band structure method for crystal. And here's these reasons. First of all, we talk about the electronic properties of some TFM systems. And you can see here in the diagram, we have two group of reasons. Now we just talk about the material is gallium manganese arsenide. Its Curie temperature get to the square root of C. C is the concentration of manganese atoms. And this kind of TC curve is related to double exchange mechanism. I mean magnetic double exchange mechanism. And the other one is the gallium manganese antimony. Yeah, and its high Curie temperature is related to C. And this character is depend on the magnetic BD exchange mechanism. And if you, when we have to more in detail about this kind of mechanism, we use Heisenberg model plus with Lichtenstein formulation to understand the mechanisms. And finally, we figure out that double exchange mechanism has strong but short range interaction. And the other BD exchange mechanism, it has weak but long range interaction. And how about the calculation TC Curie temperature? We recognize that when we calculate the Curie temperature, we have to pay attention about percolation problem. So here we talk about percolation problem combined with Monte Carlo simulation method. And finally, we have experimentally suitable reasons. And you can see here in the many diagrams, diagram regions. For example, you can see the red dot is either reason for experiment. And the blue dot is the reason for Monte Carlo method combined with percolation problem. And the others. And finally, you see that the result of experiment and the result of Monte Carlo simulation are mostly the same. And continue, if we look at this diagram, we will see that because many Curie temperature of this DF and DMS system are so loud, and so it cannot use in the real life. We have to increase the TC. But in this diagram about gallium manganese arsenide, you see we can increase the TC if we increase the concentration of manganese. But we cannot do that because GMS system typically concentration around 10% only. So we could not have high TC in GMS system. And on GMS system here, just homogeneous magnetic impurity distribution DMS. And now we look at inhomogeneous magnetic impurity distribution EMS. And this kind of DMS we have already in the real life. You see there are two examples of this kind of material: aluminum chrome nitride with gram 7% concentration, or gallium chrome nitride with gram 3% concentration, and they have so high TC temperature is about 900 Kelvin. And in this kind of material, we pay attention is electronic or magnetic property. We have to use generalized perturbation method to pay attention in the chemical interaction between manganese impurity, and then we use Monte Carlo methods to build the columnar structure. The columnar structure is a kind of impurity concentration in the DMS system. And finally, we use the method proposed by Dimitrov to simulate the variation of hysteresis in superparamagnetism phenomena in the gallium manganese nitride. And in conclusion, we see that by controlling the inhomogeneity of impurity distribution in ETMS, we can control the magnetization process in the materials. And then about my opinion in this session. In this session, I think it's so wonderful for me, but I have a question here. I figure out this diagram, and I don't know how we have the minor strength interaction here, and the lecturer, the professor said, maybe the professor said had not yet talked about that, and I wonder about that. Yeah, the second section I pay attention now is the surface interface as a playground or foundation, realizing designer materials and process. And I figure out that there are 5 using of surface interface. The first one is we can use surface as a catalyst for a certain interaction. And yeah, well, the relative, in this section talk that the relative position between hydrogen molecule and the surface or a strength in the surface and fix the orientation of hydrogen molecule can make the potential energy surface change dramatically. And from these reasons, we conclusion that every reaction follows a certain potential energy surface. In other words, if we change the potential energy surface, we can have the dry products from a certain reactions. And the second usage of the surface in related to the surface, that means we can prop the surface by using hydrogen molecule. For example, in this session, the session talk about nickel aluminum 110 and copper 3 platinum 111, and they figure out that we can distinguish this surface by comparing the dissociation dynamics of hydrogen molecule about this surface. And the third usage about the surface is we can use the surface to align molecule hydrogen molecule. It means that hydrogen molecules can be aligned by surface to 2 ways. These molecules go through or scatter in the surface. And the fourth application of the use related to surface, that we can store hydrogen molecule by surface. In the nature, the ratio between octal hydrogen molecule and the para hydrogen molecule is about 3:1. And this situation is dangerous to store or transport hydrogen liquid in the real life. Therefore, we can use ionic surface as a scattering or filtering media to change octal hydrogen molecule to para hydrogen molecule. As a reason, the new ratio is about 1.5 or even 1.16 by SRTE TiO3 surface in different terminations. And the last application of using here we can use surface. We can use surface to produce efficiently hydrogen ions. If we put hydrogen molecules near the sunchain 110 surface, we will have an interaction between them. Because of the difference in the work function, there are some electrons move from junction surface to hydrogen molecules. At present, we have some hydrogen atoms. And finally, I hope the Professor Daniel can talk more clearly about simulation conditions and Hamiltonian for each problem here. And this is I stop my talk now. Thank you for listening.
Thank you very much, Ms. Yanmi.
Yeah.
So that's Ms. Yanmi from OUICP student.
Yes.
And I saw that you explained about the research regarding related to Professor Dino research, right?
Yes.
Or supervised with, by Professor Dino. And Dino Sensei already here with us also, right? Do you have any comment, Dino Sensei, about Yanni Sang presentation?
Yes, thank you very much for the nice summary of the lecture. And because we don't have time, so you can, with regard to your request for more clear simulation conditions and Hamiltonian, please so contact me directly by email.
Yeah, thank you. Yeah.
You know my email address.
Yes. How can I have your email address?
Yes, so please contact me directly and then we can discuss. I can give you more information.
Yeah, thank you. Yeah, this section is so important to me because I do something related to surface. Thank you for your session. Thank you very much.
Thank you very much.
Thank you, Dino Sensei.
Yeah.
Thank you.
Is there any question from another participants for me?
Maybe no.
No.
We can continue.
Okay.
Due to the time, I'm sorry.
We can continue to the next presenter. The next presenter is M. Noval. He will give a review about the Professor Brian Yuliarto's lecture.
Yes, okay.
So please start your presentation. 5 minutes.
Good morning,
5 minutes.
everyone. Good morning, everyone. My name is Muhammad Noval from Physics Department of IPB. Today, I would like to present my review of the lectures by Professor Brian Yuliarto of ITB. Nah, the lecture is titled Introduction to Materials Gas Sensors. And I would, before we go to the techniques, I would like to introduce some background. First, air pollution is a very serious problem. The WHO says that air pollution causes as much as 2 million deaths in the Southeast Asia region per year. But one problem is for many gases or chemicals that causes air pollution, we can detect it. We can use our sensors to detect it. So this is what makes air pollution so much dangerous. So we must take steps to reduce and or to eliminate this problem. But first we must know how much we emit in each activity we do. Now, to solve this problem, we should have a counting and detecting device to detect how much air pollution we emit of in each activity each day. This device is called a sensor. Namely, if we are talking about air pollution, it is about gas sensor. Nah, these are the desirable characteristics for gas sensors. Fast response. First is fast response. What is fast response? Fast response is ratio of sensor resistance before and after the exposure of the gases. High sensitivity is the high gradient of response, the concentration curve, and high selectivity. which means the capability of sensors to distinguish different gases, long lifetime, optimal temperature. So the temperature when the sensor deliver maximum response, this depends on whatever gases we want to detect. Resistance to humidity, phase recovery, how fast the electrical property return to initial conditions after being exposed to the gas. In a sensor, it is usually the resistance of the sensor. And high response. High response is measuring the signal generated when a sensor is exposed to the gases. Yeah, this is the structure of a gas sensor. In the lecture, Professor Bian talk about the most important part of this sensor, namely gas sensing layer. Yeah. Now, what is a gas sensing layer? Gas sensing layer is the one that actually responds when it was exposed to different gases. There are two types of gas sensing layer, namely made of metal semiconductors or MOX and carbon nanotubes. In this lecture, we'll talk only about the metal semiconductors. Nah, before we talk, there are two types of metal oxide semiconductors, namely N-type oxide semiconductors and P-type oxide semiconductors. In the N-type semiconductors, it has a semiconducting core and it has low resistance and have in the outside an electron depletion layer which has high resistance. While in the P-type oxide semiconductors, it has insulating core with high resistance and hole accumulation layer which has low resistance. Now, this is some of the advantage and disadvantage of the metal oxide sensors. Metal oxide sensors have high sensitivity, low cost, is very easy to manufacture, have compact size, and have good chemical stability. However, these sensors have low selectivity, low humidity resistance, high operational temperature, high response. I think it should be in the advantage column. And so yeah, I'm sorry. Okay, this one. Okay, and high power consumption. Next, performance of the gas sensors depends on the resistance of the sensors. Yeah, there are in the total resistance of the sensor, there are three parts, namely vertical boundary, surface, and bulk. The contributions of each of three can be compared to the contributions of total resistance in a system, in an electrical circuit. So particle boundary, so surface and bulk system resistance made a parallel circuit, while particle boundary made a serial circuit. Yeah, this is the working principles of N-type metal oxide semiconductors. We can see when it was exposed to air or oxygen, this cause there are no air shell. There are no shell resistance. It only consists of core resistance because when it was exposed to when it was exposed to air, there are air core and air shell. So it means there are core resistance and shell resistance. While if it was exposed to an reducing gases such as carbon monoxide, the shell resistance disappears. Which means the conducting band decreases. While the P-type metal oxide semiconductors has different mechanism of work, but while when it was exposed to air or oxygen gases, the resistance is, and when it was if we compare it when it was exposed to other gases such as this is methane. No, not methane. Organic gases. I forget organic gases. It makes the potential barrier to increase. Okay. Now there are some strategies to improve the performance of this type of sensors. Namely, sensitization with doping of halovalent cations, chemical sensitization with loading of noble metals, control of the morphology, loading additives, P-type additives to N-type oxide semiconductors, longitudinal oxide P-N junction, made nanocomposites between P and N-type oxide semiconductors, and made P nanoclusters on one dimension N-type oxide semiconductors. Okay, and that's all I have today. Thank you for your attention, and terima kasih.
Thank you very much for Noval for the presentation. Is there any question for Noval from our participants or sensei or professors who join with us?
Hello.
Hello, Mr. Hello, Sensei Yoshikawa. Hello, Sensei.
Hello. So, what useful information can you get from this lecture for your research subject?
I am interested to extend the principles of the sensors for detecting other chemicals such in different conditions, such as in marine conditions or in the water, or or airborne particles.
Oh, so your research subject is also sensor?
No, to be as of today, no. But I am simply interested in this topic.
Oh, I see.
Are you third-year student?
Oh, sorry. Fourth year.
Fourth year. Okay. Thank you. The next presenter is, we would like to call Sarah.
Sarah will give a presentation about the lecturer from Dr. Damar. Dr. Damar Adika also joined with us today. So maybe after Sarah's presentation, Dr. Damar can give any short comment for Sarah. So Sarah, if you're ready, please start your presentation.
Okay, thank you very much. I will prepare the slide first. Okay, so can you see my slide?
Yes, we can see.
Okay, good morning, everyone. My name is Sarah. I'm from ITB, taking nanotechnology program. And in this occasion, I would like to give a review from yesterday's lecture given by Dr. Damar. The topic is about Introduction to Materials Characterization. So why we need to learn about this material characterization or the device itself? Because it can help us to obtain information of the material's properties, for example, physical or chemical, in which we cannot be observed without the help of the devices. For example, we would like to know the crystalline structures, which cannot be observed by our naked eyes. And from yesterday, Dr. Damar categorized the characterization devices into four. The first one is microscopy, where we can observe invisible object, for example, the material structures. And the result, we can get the image, which can be also directly interpreted. And one of the device example is the TEM. And the second one is spectroscopy, where we can study the object response in regards to the electromagnetic radiation given. And the result, we can get the spectrum that usually need further data analysis for interpretation. The example of the device is TM, and this is the result. The third one is diffraction method, where we can identify based on the crystalline structure, what are the elements that are contained in our sample. For example, we can use XRD and the result is like this, which is the diffractogram or diffraction pattern. The last one, using thermal analysis, we can measure the heat properties of the sample, such as heat flow or the reducement in mass during sample heating. The result is spectrum, and the device we can use TGDTA. And in this session, I would like to going deeper to the first category, which is the microscope, which is also divided into three. The first one is the optical or light microscope, where we use the source of the light, whether it is a white light or fluorescence light or laser, as in the light microscope, where we can measure reflection, diffraction, diffraction, and reflection of the source radiation. The second one is electron, where we use the electron beam as the source of the electromagnetic radiation, as in SEM or TM. The last one, we use the probe to scan all over the sample surface, as in AFM and STM. And in working with microscopy, we should pay attention to the one parameter called resolution limit, which has definition, the ability to resolve two distinct objects. And there are two equations describe the resolution limits. The first one is arbitrary, and the second one is by Rayleigh, where the resolution limit, or D or R here, is determined based on the wavelength of the source light. But what about if we have the electron as the source? So yesterday we have also been introduced to the wave-particle duality. So in Young experiment, we can see the interference phenomena, where we can regard light as a wave. And then in the photoelectric effect, Einstein explained better that the light is a collection of photon particles in the photoelectric effect. So this means that a light is also a particle, because the energy of excited electron is dependent with the frequency of light, not from intensity. And then de Broglie hypothesized the opposite of the photoelectric effect here, that state particle is also as a wave. So any particle, or in this regard is electron, that has energy and momentum is the de Broglie wave or frequency f, and has a wavelength property. So we can use electron as the radiation source in our microscope, as in the SEM and TM. And by using electron, we can also get better resolution. And here you can see some of the parts that construct the TEM and SEM. And overall in SEM, we can observe surface morphological structure, while in TEM, we can going further into the internal structure, but there are also some sample preparation that need to be done. For example, we need to make the sample very thin so that the electron beam can penetrate the sample. And about the electron and sample, the interaction itself, we have to pay attention to it. What interaction that happens, whether it is inelastic scattering or elastic scattering, and what types of electrons that are detected by the detector, whether it is a secondary electron or backscattered electron. And this is the example image of the CEM, while also in CEM, we can combine the device with EDS, so that we can get this graph or spectrum that describe what are the other elements contained in our sample and how much the percentage. So yesterday also we are given the guidelines. We are shown the video how to prepare or using the ACM and TM, and first doing the sample preparation for SEM. We can also do metal sputtering for the sample which is not conductive. And while for TM, we should make the sample very thin. For example, we can use ultramicrotomy, and then we were shown how to set up the device and how to load sample, and usually the vacuum environment are needed, and how to optimize the image by setting up the focus, contrast, magnification, and the other until we can get the observation. So these are some of the results which were given yesterday. And to conclude, so we have shown and explained by Dr. Damar how to understand the working principle of some materials characterization. In this regard, the SEM and TM with the differences you can see further in here. So that's all from me. Thank you very much for your attention, and I would also like to thank all the lecturers and committee for conducting these courses. I really enjoyed the courses, so thank you very much. That's all from me.
Thank you very much, Sarah. So is there any comment from Dr. Damar? Dr. Damar here join with us today.
Okay, thank you. I think the summary is already very good. She shows a clear understanding about the topic. Maybe in the last slide, there is a difference between SEM and TEM. The TEM viewed in the projector, the fluorescent screen, yeah. But it's not always like that. We can also connect a CCD camera and then connect it to the monitor as well for TEM. Maybe only that is my comment. Thank you.
Thank you very much, Dr. Damar. And thank you very much also for Sarah. We will continue for the presentation. So now we will invite the OUICP participant named Chu Toi Nam. So Chu Toi Nam, can you hear me?
Yes, I can hear me.
Okay, so Chu Toi Nam or Nam Sang will present a presentation today, this time. So if you're ready to start your presentation, please start your presentation for 5 minutes.
Yeah, thank you so much. You can see the presentation.
Yes, we can see your presentation.
Now I begin my presentation. And today I am report the introduction to computational material design, because now I talk to two major, either carbon functional nanomaterial, and second either strongly coordinate and superconducting material. And now the first is the section 4 is carbon functional nanomaterial. And the first is I want to introduce the carbon nanotubes among the nanocarbon material, including the graphite, diamond, BCS, fluorine nanotube, and graphene. Before the quantum mechanics, we only know about the graphite, but now people create more the material by graphite into collision compound of the carbon material and find out if the natural carbon nanotube. The difference of the atom configuration make a different property of the material. For example, graphite. Graphite is a form hexagon network, while the diamond is from the three-dimensional lattice structure, so that the material is different in the property. Graphite is very soft, and diamond is very hard. It hardest is the material. Second, I want to give the basic theory of applicable for nanocarbon system by quantum mechanics. To know electronic structure of graphene, it's merged from the lattice structure. Graphene from the honeycomb bipartite lattice structure. You can see here, each structure creates the direct Dirac point at the Fermi energy that is equal 0. You can see the here K is the Dirac point, and so with the number is the K per A equal the 2/3 P. The decreasing of electron in graphene is described in relative this Hamiltonian called Dirac Hamiltonian. Nowadays, using the several heuristic methods, design the zero method most by adopting the chemical designing method to find the spin effect, perfect constant for graphene nano response, and the first magnetism with a strong magnetic moment in nano response, and the other interesting application. And nowadays the FT technique with the fundamental tool for the design of the carbon material among the various techniques in the theoretical simulation. It allows users to even consider an extreme condition at high pressure, eternal strong bias voltage, control the electric density, and kind of field effect doping and as well. And now I introduce some example of material modeling and design. The first, carbon nanotube using the simulation of the gas bias semiconductor system by ESA method. This method depending side of bias voltage. The researcher can control the effect doping in the both electron doping and hole doping direction, so that it is suitable with application material. However, one problem for this method is a website. Nickel graphene used to solve this problem by nickel sandwich structure. The second example is the energy storage by lithium-ion battery by replacing the electron with carbon-based material with lithium-ion capacitor. Lithium capacitor created by harsh carbon material and activate carbon fiber. The energy density per volume of the lithium-ion capacitor is better output performance with not electron potential at the positive electron and state negative electric potential. This is the effective the lithium-ion capacitor than the lithium-ion battery traditional. The third is an example for the hydrogen storage application by hydrogenation reaction by using the 3 hydrogenous graphene vacancy. However, because the dehydrogenation process is endothermic, so energy loss more by a very nice activate barrier to prevent the use of organic hydrogen. So that researchers using the 3 hydrogenous graphene vacation used to solve this problem because it reduces the energy barrier to only 1.3 electron volt, so that no energy consumption in the hydrogenation state in hydro storage processing. Second is I want to do the section 6, strong correlation and superconducting material. The first, I want to definition superconductivity is a phenomenon in which resistivity of material disappear this appear is a certain temperature that is a superconducting transition temperature called TC. And now using to show the design superconducting and using the BCS theory or Batten copper differ theory is the first microscopic theory of the superconductivity since Heiko Kamerlingh one in the 1911 discovery. The theory describes superconductivity as a microscopic effect caused by consideration of copper pair. At the sufficiently low temperature, actually near the Fermi surface become unstable again, the formation of copper pair. In conventional superconductor, an attraction is generally attributed to an electronegative interaction. The BCS theory, however, requires only that the potential be attractive regardless of its origin. In the BCS framework, superconductivity is a bosonic property and boson sufficiently. Yes.
Okay. Okay, because we lost you for a while, so please continue.
Yeah, thank you. Can form the Nash boson as sign condensate. Superconductivity were simultaneously explained by Nikolai Bogoliubov by means of the Bogoliubov transformation. And now BCS derived several important theoretical predictions that are independent of the detail of the interaction in the quantitative prediction mentioned. We know how for any sufficiently weak attraction between the electrons and the Nash condition is fulfilled for many low temperature superconductors. The electrons are born into copper pair and their pair are coordinated due to the Pauli exclusion principle for the electron from which they are constructed. And the value of the energy gap delta at the temperature T on the critical temperature Tc. The ratio between the value of the energy gap at the zero temperature and the value of the superconducting transition temperature. And finally, the BCS theory reproduced the S-stop effect, which is the experimental observation that for the given superconducting material, the critical temperature is inversely proportional to the mass of the isotope in the material. And now I will show the one example to the different superconducting is the different isotope. You can hear the -3 plus is a particle repelled by strong C2 plate. The valent copper agree, which respond to the reaction by in the number of electrons. So now you can hear the.
You have 1 more minute.
Yeah. You can hear the two different superconducting material, either by Nassif and mercury. TC of two plate by natrium with TC about 40 Kelvin and mercury with TC higher 90 Kelvin. Lithium couplet had TC lower because it is actually the Z square contributing near the Fermi level. And now the finally is some summary is the cost and learn the how to discover novel material with the third property function so that inverse problem to design material structure and composition. Second is to know the basic principle and method to create new material. And second, third is the application of material design for the night about energy, reduce environment pollution. And so I think it is the premise for study and research method. Thank you for your attention.
Thank you very much for your presentation. So very interesting. But we need to continue to our next presenter. Next presenter is Mr. Satria Hidayat. He will give a review from lecturer from Dr. Pong Viet Bach. Mr. Satria, are you ready?
Yes, wait a minute.
So anytime you're ready, please start your presentation.
Okay. Can you see my screen?
Yes, we can see.
Okay, hello everyone. My name is Satria Hidayat, and I will present a review of a lecture by Dr. Pong Viet Bach with the title Gas Absorption on Surface of Graphene and Graphene on Substrate. Okay, first, what is graphene? Before we go there, we know that for zero-dimensional structure of carbon nanomaterial, we have carbon-60 or fullerenes. And for one-dimensional structure, we have nanotubes or nanorods. And the graphene we discuss here is a two-dimensional structure of carbon nanomaterials. And we also have graphite for the bulk or 3D form or of sp2 bonded carbon atom that arranged into a rigid honeycomb lattice. So the graphene is two-dimensional carbon nanomaterials of sp2 bonded carbon atom that arranged into a rigid honeycomb lattice, just like shown in here. Okay. Dr. Pung used graphene due to its several properties, and maybe some of us know that graphene has high mechanical strength and extraordinary electron transfer capabilities. Graphene also has excellent electrical conductivity and chemical stability at ambient or room temperature. All the properties I just mentioned makes graphene an ideal candidate for gas or vapor detector or sensor. In here, we see that semiconductor material in here has a certain amount of gap between the conduction band and valence band. But on graphene, the gap is extremely small, so that electron can move very easy and very fast between the band, resulting in graphene's excellent electron transfer capabilities. Okay, the objective of Dr. Pang aims on conducting the study. The first is to learn interaction between graphene and substrate for gas sensor design materials. The second is to understand the absorption mechanism of toxic gases on the heterostructure. And the last is to know the selectivity and sensitivity of gas sensor of graphene-based materials. We can see on the right hand side here that the configuration of graphene here and here on the hexagonal boron nitride here and on silicon dioxide. Okay, from the first principle DFT calculation using different van der Waals functional, Dr. Pung conclude that graphene is a weakly bound to hexagonal boron nitride and on a silicon dioxide surface with the binding energies, as we can see here, is around 0.85 up to 1.18 electron volt, which are typical for van der Waals heterostructure with distance around 3.2 angstrom. Okay, the next is, you can see here from the density of state here that the interaction between hexagonal boron nitride and graphene and on silicon dioxide with P and P antibonding state of the carbon atom in the graphene breaks the symmetry, as you can see here that small band gap occurs at the Dirac cone. For the graphene on hexagonal boron nitride, we get a band gap of 50 milli electron volt, and on a graphene on silicon dioxide, we have 120 milli electron volt. And here is the absorption configuration of toxic gases that we study, Dr. Pang study on the graphene-based heterostructure, where the gas molecule absorb have a toxic gas molecule absorb have a parallel orientation with respect to the planar surface of the heterostructure. Here, the above one is graphene on hexagonal boron nitride, and the lower one is a graphene on silicon dioxide. The toxic gases molecule are weakly bound to the substrate, having the absorption energies which are typical for viscissuption. We can see here that the absorption energy are between 0.15 up to 0.31 electron volt. We can also see here that in general, graphene associated with silicon dioxide, the maroon one, I think, with silicon dioxide substrate have a better sensitivity detecting toxic gases than graphene associated with hexagonal boron nitride. And for selectivity, nitrogen dioxide tends to absorb better in here than the others for all cases of substrate on silicon dioxide or hexagonal boron nitride. Even though it isn't clear any further study on how the substrate improve selectivity. And for charge transfer result, it shows that all toxic gases act as electron donors on graphene-based substrates. In general, by introducing different substrates like hexagonal boron nitride or silicon dioxide, there is enhancement in sensitivity of graphene-based gas sensing materials. So the conclusion we have, Dr. Pung have, is that toxic gas molecules are weakly bound to the graphene-based material, having the absorption energy which are typical for viscissuption between 0.15 and 0.31 electron volt, as I mentioned before, and at a distance in the range of 3.2 up to 3.6 angstrom. The second conclusion is that interaction between hexagonal boron nitride and graphene on silicon dioxide with a bonding and p antibonding state of the carbon atoms in graphene break the symmetry of graphene, and a tunneling band gap occurs at the direct cone or a direct joint. And the last conclusion is that the enhancement of sensitivity and selectivity, we have that hexagonal boron nitride and silicon dioxide enhances the sensitivity of graphene towards toxic gases better than graphene itself. For the future work, Dr. Fung suggested to investigating the enhancement of selectivity of graphene-based gas sensing materials by introducing different substrates such as gallium arsenide. This is SN dioxide, or other van der Waals heterostructure, or we can also add a defect or a doping transition metals on the graphene. That's all for me. Thank you very much.
Thank you very much, Mr. Satria, for your presentation. So we will continue to the next presenter. The next presenter will be Diki Setianto. Diki Setianto will present a presentation regarding review of a lecturer from, I'm sorry, for a minute, from Professor Kazuyuki Sakamoto and Professor Yoshitada Morikawa. Okay, Diki Setianto, are you ready?
Okay, let me try to share screen first, okay?
Okay.
Could you see the slide?
Yes, we can see the slide. So you can start your presentation and time is 5 minutes. Thank you.
Okay. Assalamualaikum warahmatullahi wabarakatuh, and good morning for everyone. I hope you have a good day. So in this opportunity, I will give you my presentation about the review of atomic layer materials formed on solid surfaces, investigating exotic physical phenomenon for non-science and nanotechnology lecture session, and stage scenery hands-on session. And my name is Diki Setianto, and I'm from Engineering Physics 2018. I'm a third year undergraduate student. Okay, the first topic is about the atomic layer that has been delivered by Sakamoto Sensei. So before I start to present the review, please accept my apologies if there will be any mistakes because I'm a newbie in this. Okay, so for the summary, Sakamoto Sensei gave us a lecture about the atomic layer material. But what is the definition of atomic layer material? So atomic layer material, or ALMS, are the new class of materials that really close to a truly two-dimensional system as we can achieve. Okay, so what is two-dimensional system? Why is it matter from the first time we talk about two-dimensional system? So ALMS is offering an interesting physics due to their low dimensionality and have been shown to be useful in creating highly efficient photodetectors, integrated circuit, and other optoelectronic devices, such as you can see at the left side of the presentation. You could see that the example of ALMS is such as graphene or TMDS and HBN. It could be used such as ultra-thin devices and low power consumption, high-speed devices, and of course, high efficiency optoelectronic devices such as solar cell and any other devices, of course. So actually, what is the key of this wonderful material, of this wonderful physical properties? Yeah, the key is in their properties itself, the properties of the LMLS. Okay, the two-dimensional, their properties of their low dimensionality could be used such many functions. And the fourth point is that photoelectron spectroscopy. Yeah, so Sakamoto Sensei, after he delivered the first topic about the properties, about the physical properties of LMS, is delivered the second subtopic that called it delivered about photoelectron spectroscopy. So my summary about it is photoelectron spectroscopy is used by using photoelectric effect and synchrotron radiation to measure binding energy of electrons. Okay, there's so many other use for the photoelectric spectroscopy, but for the time, because the time is limited, I will go on. So after Sakamoto Sensei delivered about photoelectron spectroscopy, he delivered to about Rashba effect. So the point that I got a bit, from Sakamoto Sensei lecture is that Rashba effect will direct to makes possible to tune the spin direction of ALMS and creating a combination of spintronics and velitronics, which make it possible engineering the spin. So if you see the left side, there's a picture, the comparison about the Rashba effect and Zeeman effect. As we know, they're both is engineering the spin. I mean, and you can see the Rashba effect is what is it? The angular factor, just like that, and Zeeman is like to the x-axis and negative x-axis. And then after delivering about the Rashba effect, Sakamoto Sensei delivering about topological insulator. Actually, I don't really get it about this topic because in my major, actually, I'm not studying this. So the point that I get is that novel charge doping method for topological insulator is to make possible to functionalize the eye. Okay, so and next Sakamoto Sensei delivered a lecture about semiconductor. Actually, it's about rubrine semiconductor. So here's what interesting about the rubrine semiconductor. Rubrine semiconductor is really different from common semiconductor because when Sakamoto Sensei delivered the lecture, he said that the whole transport mechanism between the common semiconductor and the rubrine semiconductor is totally different. If we study about the whole transport mechanism of the common semiconductor, it's the whole is transport like translational. Translational. And if we're studying about the rubrine semiconductor, the whole transport mechanism is hopping or vibrational mediated. And here's what interesting about it. Okay, that's the first topic. Okay. Okay, the next topic is about state scenery hands-on session. It's from Morikawa Sensei, and I know he is here with us. So before I start to give my review, once again I wanna give my apologies if there was any mistake, Sensei. If there will be any mistake. Okay, so my summary, state scenery is actually a simulation tool for computation, which is used to do structure optimization, finite temperature, molecular dynamics, reaction path search, ASM, to calculate electrochemical reaction and electric field effects, and also vibrational spectra, electronic states, and STM image calculation, which is already delivered in the lecture by Morikawa Sensei. Okay, and then the next is the feature. The feature of the state scenery itself, it will be using a density functional theory, which is so many variant like LDA, and then generalized gradient approximation, GGA, and GGA plus U, and of course, plane waves such as P, DW, and DF. And then ultrasoft pseudo potential, and then plane wave basis set, iterative diagonalization, Broyden charge, density mixing, and the state scenery itself is using Fortran 90 plus MPI plus OpenMP. So the point is what I pin is about the pseudo potential. Okay, so the next topic is I'm trying to give a review about the explanation of pseudo potential. Actually, there was many things that explained by Morikawa Sensei, but not I don't get it all the topic actually, because I'm just studying quantum mechanics in last semester. So once again, I'm sorry. So the brief explanation of pseudo potential. The concept of pseudo potential itself, that if you see the left side, you could see the image.
You have 2 more minutes.
Okay.
I'm sorry.
You could see the 2 image. It's basically I took from Morikawa Sensei PowerPoint. So the concept of pseudo potential itself is you could assume that atom is scattering potential of electrons. And then the next point is core electrons are localized within spheres of radius Rc are the same as those through atomic potential. Then the valence electron states should be reproduced by pseudo potential exactly. And then for the non-conversing pseudo potential, the formula is using consum. And it's like other quantum mechanics. We should search the energy eigenvalue for by using Schrödinger equation, but this time it's many body problem, so we use consum. So to construct non-conserving pseudo potential, we first perform all electron calculation for an insulated atom and obtain energy eigenvalues, wave function, and self-consistent effective potential. And you could see there is an L variable is an angular momentum number of valence state and satisfy consum equation as I already told you. Okay, I think that's all from me. Thank you for listening, and thank you very much for the committee already held these wonderful courses. Thank you.
Thank you very much for your presentation. Morikawa Sensei, do you have any comment, short comment maybe?
Thank you for reviewing our lectures. I think both Sakamoto Sensei's lectures and my lecture, the knowledge of quantum mechanics is necessary. So for a bachelor third year student, like Dicky-san, maybe these lectures may be difficult, but I hope you will learn more deeply the quantum mechanics and the research related to these topics. Yes, please continue learning quantum mechanics. Quantum mechanics is getting more and more important in real technologies. Yes.
Thank you very much, Morikawa Sensei.
Arigato, Sensei.
So we will continue for the next presenter is Le Pho Puang Tuan. I'm sorry if I misspell your name, Mr. Lee. So are you ready for the presentation? Hello?
Yes.
Oh, Miss Lee.
Hello.
Okay, so she will give a presentation to review the lecture from Professor Nguyen Tan Thien. So please start your presentation if you're ready. Hello?
Yes.
Okay.
Good morning, everyone. I am Phương Thong. Today, I present our research about absorption of small gas molecule on the edge of substance graphene nanoreformed graphene nitrogens. Electronics and transport property of substance graphene nanoreformed graphene nitrogens with short as gas molecule are deployed by post-critical calculations based on CFTs and non-equilibrium string functions using the ATK software package. To get the sensing capabilities of pseudospectral nanoribbons definite nitrogens for gas molecules such as carbon monoxide, carbon dioxide, and ammonia. The absorptions of gas molecule were investigated on the edge of pseudospectral nanoribbons definite nitrogens as the edge of ADS is the most reactive site in the response yes to the region of daily functions. Figure 1 shows three possible one side on the edge of the pseudospectral nanoribbons definite nitrogens. Removing passive hydrogen atoms at the top of the carbon atom. B. Removing passive hydrogen atom at the top of the nitrogen atom. C. Removing passive hydrogen atom as the top of the C. Removing of passive hydrogen atom on the edge of the response. On three sample, we investigated absorptions of CO and CO2 and X-rays after optimization, which show three models in the figure 2. For determining the most referred sample, we calculated absorption average. As per this definition absorption here, negative absorption energy exhibits that process is short-term in nature, while the magnitude signifies the monatomic stability. The absorption energy of pseudospectral nanoribbons definite nitrogens across CO is the lowest. It's the obvious that CO absorption is the most stable one. In on-tree absorption case, the nucleus S atom of pseudospectral nanoribbons definite nitrogen to get molecule in carbon atoms rather than nitrogen atoms. The absorption distance of CO2 and absorption nitrogen pseudospectral nanoribbons definite nitrogens are more capable of chemical absorption, while ammonia absorbs pseudospectral nanoribbons definite nitrogens is more likely to absorb physically. The electronic property of pseudospectral nanoribbons definite nitrogens were studied to understand the sensing capabilities to CO2 and Hysteresis. The density of state ensembles are shown in figure 3. In figure 3, we see that after the absorption of gay molecules, the density of space of system change and the band gap on the three sample expand. The band gap of CO absorbed Saltus benzalaphen nanoribbons in nitrogen in the last in race. The figure 4 shows IVQ for IG field of a short sample and the poor sample. We can see that this line is similar when biased from 0 to 1.4 or 1.6. The current value of the sample are almost zero. They react a bit as the 1.8 and degree after that. Comparing to poor sample, the maximum current of a CO2 absorption sample is the most 45 times greater. In the summary, as absorption of CO and CO2 molecule are more analytically favorable compared to S absorptions of ammonia. The absorptions of CO and CO2 on Saltus benzalaphen nanoribbons in nitrogen S shows chemical absorption. Meanwhile, the absorptions of ammonia show physical absorption. The current IV characteristics have also been investigated using the non-equilibrium functions approach. The research indicates that the conductions of the CO, CO2, and H3S absorptions Saltus benzalaphen nanoribbons in nitrogen can be distinguished as bias voltage of 1.8. Well, that is remains. Thank you for your attention.
Thank you very much for your presentation. So maybe we still have one short time for one presenter. So from OUICP student, Lan, are you ready to present your presentation? Can you hear me, Lan?
Stop there.
Hello.
Ngo Thian Lan, can you hear us?
Yes, can you hear me?
Yes.
Yes, please.
Can you present?
Your turn.
Yes. I
So
prepared my presentation about let me see. Okay. I am going to summarize about the computation material design. Can you hear me?
Yes, we can hear you. So please start your presentation. 5 minutes.
I would like to summarize session 1 and session 7 by Professor Yo Morikawa and Professor Tamio. In session 1, I would like to tell about the density function theories. What is a density function theory? Functional theory is a computational quantum mechanism modeling methods used in physics chemistry and material science to investigate the electronic structure or nuclear structure, principally the ground state of many body systems, in particular atom, molecular, and condensation phase. It's also allowed to describe the states of an electron system according to the wave function. That's why we go to the Schrödinger equation corresponding to the density function and the calculation related to the use of this function. Yes. In this Schrödinger equation is not related, relativistic, time dependent. In this, here it's and in this molecular, the molecular consider it the system that is stable over time. And by the wave function, and the energy of the molecule are determined by the time-independent Schrödinger equation. And then in this atomic and molecular system described by Schrödinger, the method gives result consistent with the experiment. Understanding the nature of electronic structure as well as related physical and chemical property of the atom. That's right. Solving the Schrödinger equation is to find the wave function and the energy. It's very useful. It's very useful and it's a complicated job. But the solution obtained is valuable information about the atomic and molecular system under investigation. There's some point of the density function theories based on the two theorem of Hart-Benscoe, and this based on these two theorems, we can use the concept equation. There are many approximate models which commonly use standard local density method or local spin density approximation, the gradient correction method, or the hybrid method. By combine the exchange functional and correlation function, we can choose the functional to apply the DFT method. And this in session 7, I would like to tell about the potential of material informatics. Material informatics is a field of study that apply the principle informatics to material and engineering to improve, understand, use, selection, develop, and discoveries of material. In this picture, by step and step, we there are many steps to find the material, the new material. We collect the data to combine with experiment. Then we correlation by minimize the data and dimension reduction, and then combined with theories by atomistic based calculation or continue based theory. We obtain the knowledge discover such as materials cover structure in which content structure property progress relationship. And step by step with beyond this step by step sanctify the some superatom such as fluency 60 with conductivity chain under special condition hydroxide amino 13 with high electron affinity like halogen superatom pyramids gone 20 and especially for the gone to pyramids tetrahedron gone 20 can synthesis by chemical. Yeah, and it's considered as a superatom. And gone pyramids gone cluster gone cluster 20 gone cluster is fried as a superatom with a high symmetry like bandgap and closed cell, especially its chemical needs produced. Is with a hormonal gap corresponding to fluency C60. And this Bayon's characteristics of a gone 20 is considered as a superatom and firing a hot structure by substitutable as a hot. And it because the parameter of geometry it's extremely stable in electrolytic stable potential for hadrons doping. And in our group we calculate, we check the dimer of the gold with poor gold and gold cluster dope with 3D transition method. By using host gold cluster changes the centimeter, we can it could be find the ground state structure and investigation some chemical physical properties as the dopant clusters as electronic configuration or magnetic property. It is very useful for the tool for the future experiment studies. That is my presentation, and thank you for the attention.
Thank you very much for your presentation. So we apologize that we couldn't facilitate all of the presenter to present your presentation because due to a limited time. And
we would like to remind you again to fill out the questionnaire. So we already shared the link in the chat box. And also to all IVC participants, please don't forget to fill out the attendance form. Also, we already shared the link in the chat box. Regarding the questionnaire, maybe we will open this questionnaire form until maybe Sunday. So we are really appreciate if you can fill out this questionnaire for our organizing committee for better IVC in maybe in the next year.
Yeah.
So then we will have some small announcement, correct, Fitria?
Yes, we will have a announcement. So before that, we will have a closing remarks, but please fill out again the questionnaire in the Google form. Also, I would like to thank you for all the participants and the lecturers for giving us a lecture series for 2 weeks, this 2 weeks from 4 January to 15 January. And then we will reach the final program by closing from the IVC committee and also from the head of RCNN, Professor Heni Rahmawati. So before that, and after that, we will have announcement for the IVC 2020 awards. So for the head of IVC committee, Dr. Triati, I would like to give you time and place to give a closing remarks.
I'm sorry. I'm sorry.
Yeah, for Dr. Triati.
Yes. I would like to ask you. I filling the Google form, but I cannot find my name. My name is Ngô Thị Lan.
The attendance form only for IVC participants.
Yes.
Only for IVC participants.
Yeah. Okay.
For the
OU-ICP, yeah, you cannot. There, you may see your name. I'm sorry.
And you don't need to fill the questionnaire or attendance form.
Yes.
Yes.
Okay, so for Dr. Triati,
Okay.
would you please to give a closing remarks as a head of IVC committee?
Thank you, Fitria. Can you hear my voice?
Yes, we can hear your voice.
Thank you. Good morning to all lecturers, students, and all participants. I didn't notice that today is the last day of International Virtual Courses 2020. So I need to highly appreciate to all participants, lecturers, and committee that we are eventually can successfully conducted this program. So today, on behalf of committee, I would like to report a brief summary of this program. And I don't prepare a slide. First, we had 2 weeks, 10 days effective lectures. And during these 10 days, participants were actively involved in lecture series, hands-on of computational material design, and also today's presentations. And second, because we need to give evaluation to all participants, particularly to ITB students who take earning credit scheme. So we ask participants to submit review lectures and also giving short presentation today. And we have received around 20 students who have already submitted to review lectures to our emails. And we are still waiting for your submission until January 22nd. So I would like to say thank you to World Class University Program of Institut Teknologi Bandung for their financial support.
and to Osaka University, particularly to Professor Morikawa, because they already support our program, especially for arranging lecturers from experimental field, and also arranging workshop on CMD workshop. And also to Daumot University for facilitating Vietnamese participants using their high performance computer. And to universities in Vietnam and Malaysia who encourage their students to participate in these programs. We would like to apologize if there is technical problems and any mistakes before and also during these programs. So that's all. Thank you very much.
Thank you very much, Dr. Triati, for the acknowledgement and closing remarks from the head of IVC community. So now I would like to invite Professor Heni Rahmawati as the head of Research Center of Nanotechnology and Nanoscience to close this program, because we already reached the final time of this program. So Professor Heni, time and place, please.
Okay, thank you, Fitria. Can you hear my voice?
Yes, Professor, we can hear your voice.
Okay, good morning, everybody. Good morning, all lecturer mostly from Japan, also from other country, yeah, from Malaysia, from Vietnam, and also from Indonesia itself, yeah, especially from Bandung Institute of Technology. So in this very short time, but very important moment, I'm personally and also on behalf of Research Center for Nanosciences and Nanotechnology, ITB, would like to deeply congratulate to committee of this event, yeah, international virtual course, and also convey our deepest gratitude to all participants, to all lecturers, and all bodies who support this program. So finally, we come to the end, and yeah, we almost don't feel that the time is running so fast. So 2 weeks, we every day meets through virtual course, but we feel close each other. So therefore, we would like to ask all participants, all lecturers, to keep in touch, yeah, for this good moment, for the future collaboration and future activities. So last but not least, so as the head of this committee mentioned, 3 important contributor, yeah, support this event. So first is from Daumot University, yeah, Vietnam, for facilitating Vietnamese participant, yeah, using high performance computer. And second, to Osaka University for organizing CMD hands-on and arranging lecture from experimental field. And also for ITB, yeah, in this case is world-class university program. So again, I want to thank to all participants, to all lecturers, and all contributors. So this program can successfully conducted. And we hope that all students, especially, yeah, who actively participate every day. So hopefully you can get, yeah, and bring the message, yeah, from the lecturer for the all field, yeah, deliver to all of you. So hope we can meet again, yeah, in next program. Not only the same program, because summer course is conducted every year, but also for other programs. Thank you very much, and I give back the time to moderator.
Thank you very much, Professor Henny, for the closing remarks. And thank you very much once again for all participants, the registered student of IVC program, the OU ICP student who joined with us today, all the lecturers from Japan, Indonesia, Vietnam, and also Malaysia. And thank you for all committee to arrange this program. And now we've officially closed this program. Thank you very much for all attendance, and we're gonna see you next year. But before that, I would like to give an announcement about IVC Award for the student and participant who already joined with us for these 2 weeks. The committee will give 2 awards for 2 students. The first is most disciplined student goes to Domenico Michael Aditya from ITB. Congratulations. And the second is perfect attendance goes to Melsa Ros Dukut from Philippines. So thank you very much for your perfect attendance in this program. And for Domenico, also Melsa, please contact to Dr. Triati through her email in triati@fi.itb.ac.id to redeem the merchandise from IVC committee. So thank you very much for your participation, and see you again next year. And don't forget to fill out the questionnaire in our Google form. That's all from us. Thank you very much.
I think we should turn on all the camera to take a picture.
For all the participants, before we leave, please turn on your camera and we will take a picture together.
Yes, please turn on your camera. Okay, it's already on, all of you. Maybe Satria, could you take picture, or Nurul?
Yes, sir.
Yes. Okay, maybe finish. Okay, I think the photo session is finished. So once again, thank you very much also for all sensei and professor and lecturer who already participate in this program. See you again next year.
Thank you very much, all participants, sensei.